Okay, students, this is the second part of the video demonstration. Recall we had a rod of a total length L3. Fixed to the rod was a spring on the left-hand side and a damper on the right-hand side. We developed the kinematic equations that related the displacements to the free variable, which in this case was the angle theta. In other words, the rod was able to deflect by an angle theta. We figured out if it deflects by an angle theta, what distance would it stretch the spring and what velocity would it pull the damper. Based on the geometry, we worked out the deflection in which the spring would be stretched, ya is equal to L1 theta. There would be a corresponding velocity for the point at A. A is the point. And likewise, we worked out the distance b, yb, that the damper would be stretched, and we took the derivative of that, and we worked out the velocity. So effectively, we have the displacements and the velocities, and going forward, we now want to develop what the forces would be. So from your textbook, we know the fundamental equations for the spring force, which would be minus k spring, and then the damping force okay. So the spring force is minus a constant, that's your spring constant, times the distance in which the damper is spring is stretched. And then the damping force is minus a constant c, this is your damping constant, times the velocity of the damper, where the velocity of the damper is just the time derivative of the displacement of the damper. So for this particular problem, the deflection of the spring is ya. So in this case, we will say in this case, that's the vertical deflection of the spring. And for the damper, okay. So this is our equations that relate the geometry, in other words, the angles and lengths, to the displacement and the velocity. So we'll worry about the directions and the sign notations in just a moment, but for now, let's just work out the absolute values of the spring force and the damping force. We have a spring constant K, whatever the value is. We have a damping constant C, whatever the value is. Just put it into the formulas, and this will imply that the spring force and for the damper, this will imply okay. So we've got the rod, we've got the angles, we worked out the deflection of the damper, the deflection of the spring, we multiplied it by the spring constant and the damping constant, and we worked out a spring force and a damping force. Now we need to figure out how the directions work. We assume theta would be positive in the anticlockwise direction. So recall that the positive x direction is towards the right, the positive y direction is upwards, and the positive angle is in an anticlockwise direction. This is our sign notation. Let's just write this down. Sign notation. put it in a little box so we don't get ourselves too confused. Positive x towards the right hand side. So that means a positive xa would be going towards the right hand side. A positive ya would be going upwards. A positive xb would be going towards the right. And a positive yb would be going vertically upwards. We recall the definition of the angle theta in terms of the arc length as so. If we assume that the angle is fairly small, the arc length that would be approximately the vertical distance over here, and the arc length would be approximately that vertical distance. So technically, this is the arc length, it's a curve, and technically the arc length B is a curve like so. So we can, just to clarify what's going on over here, we have the point A, we have an arc length SA, and then we have an approximate distance in the horizontal direction, and we have an approximate distance in the y direction. And for the point B, we have a similar situation. And if the angle theta is quite small, this means that the deflections would use these equations. So we've got the problem. We assume the angles, whatever the angles are, 2 degrees, 5 degrees, whatever it is. We worked out the relationships in terms of the underlying equations for the geometry. So having done that, we have a spring force, we have a damping force because we worked out the velocity. Okay, so now we've got the forces, and when we have the forces, we can then use this to work out the corresponding torques about the point. But before we get to that, we first have to figure out how do we define our directions and determine what is going vertically upwards and vertically downwards and that type of thing. Using our sign convention, we assume theta is positive in an anti-clockwise direction. And then if the angle theta is positive in an anti-clockwise direction, by implication that means the torques would be assumed positive in this direction. Okay, so what that means is if we have a direction for x horizontally towards the right, that's a positive x, that basically implies that a positive force is in that direction, a positive vertical force is in that direction. So if we define our directions for the displacements, that automatically defines our directions for the forces in the x and the y, and also for the angles. Why is this the case? Basically, if we use the underlying equation, force is mass times acceleration, or torque is moment of inertia times the angular acceleration. Fx is m times ax, or Fy is m times ay, or tau is I times alpha. Because the mass and the moment of inertia are positive, if this is positive, this should be positive. If this is positive, this should be positive. So when we take the time derivative, it won't change the direction. So that's just like a sort of informal way of saying, if we define positive x is going in this way, that means the positive fx would be going in this way. If we define a positive y going upwards, that means a positive fy would also be going upwards. If we define a positive angle going in an anti-clockwise direction, that means the positive torque is going in an anti-clockwise direction. So what does that mean? If we look at our notation over here, if I have a force that is positive going upwards, I take this force, I multiply it by this distance x over here. That would mean a positive torque would be going in an anti-clockwise direction. Let's think about that. If a vertical force is positive this way, I multiply it by this length over here, then that means the torque, because of an upwards force and this distance over here, would be going anti-clockwise. So the distance, the direction of the force would define the direction of the torque. Let's look at it this way. If the force is going positive in a downwards direction and I multiply it by this distance, that means the torque would be going anti-clockwise. So in this case, on the right hand side of the point O, the point of the pivot, positive forces would be going upwards, the forces. So positive forces in this side of the rod, if the force is positive, the torque would be positive in an anti-clockwise. And on the left hand side of the pivot, point O, positive forces would be downwards. Okay, so that would basically define our sign notation. So whatever the force is, if it's positive in the upwards direction on this side of the pivot, that would then define a positive torque. On the other hand, if we look at it on the left hand side of the pivot, if the force is positive in a downwards direction, then that would mean an anti-clockwise force would be positive. Okay, so let's look at our notations over here. Let's look on the left hand side. We've got the force. The spring force is minus the constant times x. Basically, we have to define what is a positive y and a positive force and displacement. So if theta is going positive in an anti-clockwise direction, I will define the vertical deflection as positive going in a downwards direction. And I said it is L1 times theta. Is this positive? If theta is positive, yes, it is positive. Okay, then the spring force would then be minus the spring constant times the deflection, which would then give me this. Let's think about it very carefully. If I look at the problem, theta is positive in an anti-clockwise direction. Positive in an anti-clockwise direction. I am now pulling the spring down, and if I'm pulling the spring down, the spring force would be in the opposite direction, which means that it would be going upwards. Does that make sense? I think it does make sense. Let's look at it on the other side. If I define theta as positive, the deflection is L2 times theta. The velocity is there. So if theta is positive, the force would be positive in that direction. It appears to make sense. So we'll leave it over there, and in the next video we'll talk about how to convert the forces into torques, and then we will work out the resultant torque using the correct sign notation.